Okay, welcome everyone. I've been very much looking forward to this, so rather than speaking, I get to chair. So let's welcome our four speakers on stage here. And we're about to have a panel discussion looking at the current state of our languages and where they're going to go in the future. We've got a nice range here, so I'll start off by letting each of them introduce themselves so we know who we've got. Go for it, Richard.
Hello. I'm Richard Feldman. I work at No Write Inc. We make grammar and writing software for English teachers. We're a startup in California. We use Elm in production. We're the biggest Elm code base known to anyone. So the creator of Elm is my coworker, and I work closely with him and know a lot about the language design, but I should clarify that I'm not actually the language designer of Elm. A lot of knowledge about Elm and sort of front-end technologies, functional programming, things like that. And excited to talk about the future.
Joe?
Hi, I'm Joe Duffy. I was previously engineering director at Microsoft for languages. So it includes C#, F#, Visual Basic, C++. Nowadays, I'm kind of off doing a new cloud startup, but it's actually very much in the languages space as well.
Hi, I'm Brian Getz. I'm the architect for the Java language and core libraries at Oracle. So I was the lead for the Java 8 language and library features, lambdas and streams, and I'm currently working on the next 20 years of Java's life.
Hi, I'm Sylvan Klepsch. I work at Microsoft Research in Cambridge, and I designed the Pony programming language, which is an actor model language, and I work on other language things at MSR.
Oh, thank you, everyone. So I'm going to start off with a few questions to begin with, and we'll see where the conversation goes. But we'll also open it up so people can throw out questions and maybe expand on some of this later. So I want to start it off with something I kind of often think about is, where do we spend our time when we're writing code? What sucks up all our time so it takes us longer to do something? I want to kind of put it to each of the panel, what they see that problem being right now, like what they think the current state of the world is and how they see that going forward. So I'll go reverse end first.
Sure. I think sort of 5 to 10 years ago, people used to reinvent concurrency every time they were writing an application, and that was a huge problem. We still do that, but now we reinvent distributed systems every time we write an application, and it's a lot worse.
Brian?
So when I'm working on a programming problem and I'm not making progress, what I find the root cause is usually that I'm not thinking clearly about what the data flows are. And once you get the data flows right, then usually the code pretty much writes itself.
Mm-hmm.
I would say probably debugging. A lot of people don't think of debugging as sort of being part of language design, but I think, especially having language abstractions that map closely to kind of your mental model of a problem, which is why, if anybody heard my talk this morning, I'm really a big fan of kind of the actor model for distributed programming and all of the concurrency constructs that have been added. It used to be the case that there's such a gap between kind of the code you would write and what was actually executing. You weren't expressing things in a logical level. It's almost like you're doing assembly programming. And nowadays, at least you have tasks and that sort of thing. I feel like we're still in that stage with distributed programming. And then when something goes wrong, you're left kind of manually reconstructing everything that happened between when you wrote your code, the compiler got its hands on it, and then mapping it to runtime abstractions. And so I think of debugging as very much in the realm of language design.
I think debugging is a great answer. I would also say sort of bridging the gap between when you're initially shipping an application and when you're scaling it. So one of the things that we've been talking about is sort of if you hire another 10 developers, you're not going to get 10x the productivity of one developer. The more and more people you add, the less and less you get out of each person in terms of velocity. And the reason for that is just that complexity doesn't increase linearly. It sort of compounds upon itself. And so I think one of the areas that we spend a lot of our time in, even though we don't necessarily think about it that way at the time, is just that added complexity doesn't scale linearly. So I think one of the things we can get out of our languages is the ability for, maybe not to get it all the way down to linear, but at least to get the coefficient lower so that it gets less and less of a compounding explosion, the more complexity that's sort of innate to our application.
Okay, I think that's really interesting because my second question was going to be about debugging. Because I find that I'm kind of obsessed by data. I measure lots of things, and I realize that I spend a lot of my time working across many languages debugging code. We often don't talk enough about that. So I'd like to actually go back to Joe with this, because I'm a bit of a fan of his blog around some of the stuff he's talked about. And you talked about the three safeties. For me, the three safeties are a great way to avoid many of the debugging issues we face. What can we do to go forward from here?
Right, so the three safeties, sort of the Midori operating system we built was kind of based on the fundamental premise that operating systems of the future should be type, memory, and concurrency safe. And concurrency safe means free of data races. As I talked about this morning, you can never be free of race conditions entirely, but at least you can be free of data races. And to me, I think one of the things we can do is use languages that actually solve the problems by construction. That was also a big mantra. We called it correctness by construction, which is kind of a lie because you could never prove that your code was correct unless you're programming in like TLA plus or some logic language. But I think it's, I look at, one of the things that pains me is after going through that experience, looking at all the security flaws time and time again. I mean, I think something on the order of 45% of the zero-day vulnerabilities that come out in any given year are actually due to buffer overruns, which we've known how to solve for years. I mean, if people would just use type and memory safe languages, sure, there is an opportunity to get that wrong because, even Java and .NET, I mean, there's some native code obviously in there somewhere, but the less of it that you can expose yourself to, the more your programs will be correct by construction. And I love seeing more people using type and memory safe languages, especially, Rust kind of takes it to a total extreme, especially trying to solve the concurrency safety problem, which I think is, out of the three safeties, the one that is probably the least kind of mainstream. It's the most difficult, and even in Rust, you can see the great length to memory ownership that you need to go through to really solve that problem, but it's a super promising approach, I think.
Mm-hmm. Anyone want to add to that?
Yeah. So this might sound like a little bit of a snarky answer, but my favorite way to reduce the pain of debugging is to not have to do it, right? And it connects a little bit to what Joe said, which is use languages that are safe, use libraries that are well tested and building blocks you can rely on, so that you don't have to reinvent the wheel from scratch every time. But another aspect of writing code that doesn't have to be debugged is to focus on writing simple code. Write code that's so simple that you can't possibly misunderstand what it's doing. And I think a lot of developers, they sort of get caught up in writing fancy code or trying to make the code fast at the same time they're trying to figure out what it's supposed to do. And all of these sources of complexity are places where bugs can hide. So if you focus on writing the simplest possible code, it's a lot easier to get something working, to build up a good base of tests, before you start to add bells and whistles or try to optimize it, or if you have to optimize it. So by striving for simplicity, you find you have to debug less often, and that's a good thing.
I think it's really very fun that a bunch of language designers, when asked about debugging, we all immediately start talking about correctness. I'm going to do the exact same thing. I think formal verification of code it has been the future for a long time, and much like Fusion Power, it will be the future for a long time. But those techniques are getting better and better, and there are languages like Daphne and F-star built on top of the Z3 SMT solver that make it possible to write significant code that is proven to be correct. There are no debugging issues. Unfortunately, currently with those tools, it means that you spend a lot of time fighting your SMT solver and debugging the fact that it can't prove what you could prove in your head easily. But building up those tools, along with dynamic tools, I think, for example, Elm has a brilliant rewindable debugger and tools like that. Building up those dynamic tools is important, but I think building up static tools that can prove correctness, even more than just the type system and memory safety and concurrency safety, as much as I think those are absolutely critical. I think formal verification is the only way we're going to end up with widespread code that is, in fact, trustable.
So I would like to build on all of this because I'm in general agreement, but one thing that I think we don't think about is when we're accidentally making decisions that lead to more debugging later. So I'll give you an example of this. So like in CSS, if something about your style sheet is invalid, it will just sort of silently fail just on that one property, which makes it pretty easy up front to make invalid properties and not realize it. So on the one hand, it feels like it's nice. Oh, it's not blocking me from making progress. It's letting me continue. But on the other hand, what that means is that potentially later on, you're going to have some unexpected behavior as a result of that invalid property where the error was just silently ignored early on. So on the one hand, it can feel frustrating to get all these errors up front and have them block you and have it say, wait a minute, you can't progress because I found a single style that was invalid. None of your page is going to render for you. But on the other hand, having that stuff up front can save you from debugging later. So very often there's this implicit choice that you're making by choosing tools that sort of swallow errors and don't force you to deal with them up front in the ways that we're talking about. It can be convenient at first, but very often it leads you to spend more time debugging later, and you don't see that cost at first.
Yeah. And if I could just add something to what Sylvan said about formal verification. So not all of us can afford to make the effort to formally verify our code, but there's something all of us can do to get some of that benefit. And when we talk about correctness, what does correctness mean? A program is correct if it conforms to its specification. So how many of us write good specifications for all of our code? And the reason I'm raising my hand, or the consequence of me raising my hand, is why Java takes a long time to evolve. We're obsessive about specifications. The most valuable thing about the Java ecosystem is the quality of the specification for the language and the JVM. And so we take specifications very seriously, and it's the act of writing the specification that forces you to think really hard about what problem I'm trying to solve here. And even if you're not going to then try to code up these specifications in a formal verification language, just having gone through the exercise of trying to write a specification such that someone who isn't immersed in the problem could understand what's going to go right, what's going to go wrong, what's the boundary, what's the goal, is an immensely helpful thing.
Actually, can I jump in there? I love that answer. So one of the things that we did building Pony is that we started with a formally specified operational semantics and type system that was proven sound, and developed the language and the runtime from there. And there was a feedback process where the development of the runtime actually fed into the formal specification and vice versa. And I think that maybe that sounds overly nerdy for real-world application code, but it kind of isn't. You can write those specifications and do that feedback process even if you're not doing it in a sort of a strict mathematical way, and it can be hugely valuable.
I also think if you look into the future, I believe that some more advanced type systems will start to influence kind of more programming languages. And if you can bring something into a programming language's type system, it does have the advantage that some of the performance problems of using a constraint solver, for example, start to go away because you can rely entirely on local analysis. So specific example, dependent typing, the ability to actually have constraints actually expressed in your source code that limit the domain of particular values, like, hey, this is a number, and I know for sure it's between the range of 0 to 3. And the type system can prove this and do it in an efficient way. I think we'll see more of that. I also think another example, Daphne is a great language for people who haven't looked at it. It's fantastic. It kind of shows kind of what the future might hold. But it's just some of the ideas around design by contract, for example, actually being able to specify requires clause and ensures clauses and these sorts of things. And then if you couple that with compile time safety plus the potential for kind of fail fast, so treating bugs as bugs rather than letting them go silently, I do think that leads to somewhere magical, and I do expect that to start impacting languages in the future.
So speaking about the intersection of some of these things, one of the things that's interesting to me is how different organizations, different teams have different needs. So for example, let's say you're working on Java, like formal specification is very important, but of course you also have, sort of the time scale that you're working with is, you're talking about like, Java for the next 20 years. I work for a startup, so we also have the very familiar experience of saying, oh, we're going to be running out of money in 18 months, So maybe, these are sort of not all one-size-fits-all approaches, right? It's not probably not a good use of our time to write a formal specification for our software because by the time we finish it, we might be dead. With the understanding that different organizations have different needs, I think that the languages of the future are going to make it easier to make these trade-offs in an intelligent way. So maybe if you're just jamming out a prototype and the absolutely most important thing is that you get it out to your users, tomorrow, maybe you do want something like the CSS approach. But ideally, you can then start with that and then say, okay, now we can transition pretty easily from that with all the safeties gone, where we've piled up a bunch of potential bugs for later, and transition that to something that is more fail-fast, that's more reliable for the future. And I think one of the recurring themes that we're going to start seeing in languages of the future is that it becomes easier to make that swap. So you don't have to sort of sacrifice the upfront velocity of just getting something out there and building a prototype for the sake of, or you don't have to load yourself up with future bugs in order to do that.
Okay, so for me, that's all interesting. Let's make it a bit more concrete. Things that people do every day. We communicate between systems. We send messages. We encode those messages. We used to do it in XML a lot, which was pretty terrible. But at least it had some types, because you've been talking about types. We then went to JSON. We've even thrown away the types. So all this formal theory, come on, guys. Like, we seem to be going backwards rather than forwards, and we're going distributed. So how are we going to get this safety if we're just going to pass around strings with no typing information at all?
Worse is better. That seems to be what the community has decided, right? I mean, they had a number of things to choose from of how they might encode messages across the wire, and they picked, from a computer science perspective, what might be the worst possible choice. In fact, like going back to the topic of specifications, there was a great post recently where someone did an experiment with 30 different JSON parsers and found that like no two accepted the exact same language because there isn't a specification, right? But it's what the world has chosen to use.
Is it linked to debugging? Maybe people use these protocols or these encodings because they're easy to debug.
My theory is it has to do with a couple things. One is just sort of like programmer happiness. Like I noticed that your comment was like XML is like something that everybody here would agree is not fun to work with, and maybe not 100%, but probably a lot of people who've spent a lot of time with XML probably don't have the fondest memories of it. And JSON is, if nothing else, it is at least something that's relatively familiar. If you're already familiar with JavaScript object syntax, you can just sort of write it, and there's not as much to learn, which can make it more fun to work with. I think that's something that's sort of underrated in programming language design, is just like fun, user friendliness for the programmer. We are all humans. We respond to incentives, right? When our tools are more delightful to use, we tend to gravitate towards those, even if those are not necessarily as formally rigorous as other tools that are out there. Well, believe it or not, one of the most popular releases of Elm was one where it didn't have any like brand new features in terms of productivity. All it had were nicer compiler error messages. It was just, look, does the same thing as before, but now it presents them in a nicer way. And that was one of the most popular releases ever, and it really just like jumped Elm's popularity massively. Not because it was something that was more reliable than before, but just because it did the same thing in a nicer way. And I think figuring out ways for languages to be delightful while still also rigorous and reliable and maintainable is one of the challenges that is sort of starting to come up on our radars as like, oh, maybe we actually need both of these things if we want to be successful.
And so I think in this specific case, I mean, the internet has no type system, right? So with JSON and everything, we've sort of found the lowest common denominator that can kind of sort of project into every language. And I think, if you look, I think this is a gap that programming languages need to fill. I think if you look at gRPC and protobufs, from Google, which are definitely not new, they've been out for years, and Google's used them internally for years, it at least gives you sort of a type system to talk about things, a way to provide an interface that is typed and provides a little bit more static typing. Now, it's not as extreme as it could, and it's definitely a subset, closer to JSON than, say, Go's full type system. I think it's a huge step forward. And I think the more we start thinking about these systems as programs and less about kind of services that are treated differently in infrastructure that's about metadata and markup and these messy, grungy things, kind of low-level details, like you wouldn't start calling methods within your programming, passing around blobs of XML, right? So why would you do that kind of over the wire? And I realize this is getting dangerously close to like distributed Corba sort of territory, so I definitely don't want to go there. I think we've learned a lot since then, but I do think the internet can have a type system that straddles this line between being fun, being flexible, taking into account all the things we've learned around versioning, namely that you can't version things on the internet, like it's V2, it's V3, it's V4, or you deal with breaking changes. I think you wrap all those lessons learned, I think it can actually be quite a beautiful thing.
Yeah, and to pick up on the comment you made earlier about, wouldn't it be nice if our safety mechanisms had knobs that we can turn that say, like, I'm in rapid prototyping mode, turn the type system off. I'm just going to write some code. I want to see if I can get something out of it. And then once I'm convinced I've written the right thing, turn up the knob so that I can get more protection. That's a nice idea. There's been a lot of attempts at doing that with gradual and optional type systems. They haven't stuck. They're a little bit like what you were saying about formal verification, which is they've been coming for a long time now. It's like for the last 10 years, everyone's saying, well, gradual typing is the next thing in type theory. And it's like, well, I'm still waiting for it, but I'm still hopeful that we might get something out of it. But I think the mistake of adopting JSON as the language of the internet is not that we picked something untyped, is that we picked something that we can't impose any type discipline on if we want, right? That there's no way to turn that knob from fully untyped to I have, some way of validating what I accept and what I omit. And the coolest thing I've seen in this space that it doesn't necessarily work on JSON, but the approach might carry over is Clojure spec. Has anybody looked at Clojure spec? This is so cool, right? So it's essentially an optional static type system for sets and maps. So you can talk about here, I accept this, this hash, and these keys are required, and these keys are optional, and if these keys are present, then their values conform to this other specification, and it's something that you can add on after the fact. You can turn it on or turn it off in production, and it's a very nice way to bring in a little bit more reliability once you've figured out what you want your system to do. It's a really pretty example, and it fits nicely also with generative testing, which is probably like, testing is one of your other questions on the back of your envelope there, Martin. Writing specs for what your functions accept and emit means that you can write test generators that will generate conformance and non-conformance stuff. It's really pretty. So I would take a look at Clojure spec. There's a lot of really original thinking there.
So we're focusing on JSON because we sort of think that that's the way that we exchange messages. And in some sense we do, in the sense that we're exchanging application data. But far more than that, what we actually do is use IP, TCP layered over IP, and TLS layered over TCP. These things are formally specified, extensively so. TLS 1.3 is progressing extremely well. People are building formally verified implementations of TLS. Multiple companies are building such things. When we look at the incredible progress that's being made on that front, I think it should encourage us as to the progress that we can make with application data and metadata.
Going back to gradual typing, so I'm going to make a claim right now, since we're on the Future of Programming Languages panel. I'm going to make the claim, gradual typing is not the future. I think it's a failed experiment. I think, like we've seen, Clojure has a gradual typing thing, and if you, so Circle CI did an interesting series of blog posts a year apart. The first is why we're embracing gradual typing with core.typed, and then a year later, why it didn't work, and we're tearing it all out and going back to untyped. And I think what it has to do with is whether this is opt-in versus opt-out. And I think if you make typing opt-in, the result is that you end up with a lot of libraries that really are not getting the benefit of the type. The ecosystem is not designed with that in mind. I have heard of an alternative to this. I haven't personally used it, but Haskell has this. And I'm not a Haskeller, so I don't really know, but I'm aware that it has, so Haskell is type checked, everything is verified at compile time to the extent possible. But there's a compiler flag you can set that says, okay, sort of just turn off all the safeties, and anywhere you find a type mismatch, just keep compiling, but turn that into a runtime exception if that branch of code ever gets run. And so the idea here would be that by default, everything is type checked, but if you're in prototyping mode or whatever, and you're like midway through a refactor and you want to just see if something works, you can do that and sort of opt into the lack of safety. That's really interesting to me. I haven't tried it, but it does sound like a better way to approach it than the other way around with gradual typing. One thing that's sort of an interesting experience that we've had with Elm, so I don't know how many people saw my talk on Monday, but we've been using Elm in production since 2015. About 100,000 lines of Elm code and like 2 billion questions answered by students. We still have not gotten a single runtime exception from our Elm code, like not even one. And that's because of Elm's compiler, absolutely, and because of the type system and the language's design. But the idea that if we were in local development mode and we were to say, okay, just turn that off just for now while I'm doing this refactor, especially if that's going to compile but exit with non-zero exit code, so it would fail all of our CI builds and people would not check that in. It doesn't seem crazy to me that we would still have that same level of reliability while still getting to sort of have our cake and eat it too with fast prototyping when we needed it. That doesn't sound crazy to me, but when I look at what gradual typing, seems to be doing in practice, it doesn't seem to be getting there. You don't hear about gradually typed languages where people are saying, yeah, we've gone for like 2 years in production with no runtime exceptions. I never hear stories like that. So, it seems to me that it was a nice idea, but I don't think it's going to work out.
Tim Jones at Victoria University in Wellington, New Zealand, wrote a paper called "Gradual Typing is Morally Wrong and We're All Monsters Now." His entire PhD thesis was on gradual typing, and he wrote it just after finishing as a refutation to his own thesis. And it's well worth reading if anyone ever considers going down that route. Richard's right.
So this morning, Joe, you made the comment about the lines is more important than the boxes. So, because this is where we're kind of drifting off, and we're very much going into distributed computing. We're seeing advances in platforms also. We're not seeing so much advances in languages. Usually when we're doing I/O in languages, it's a pain. What's going to change? Are people caring about this?
Yeah, so what I meant by that is really, it is funny when you're focusing on, a single process system, that process is kind of pristine. The failure of that process is the end of the world. Like, you never want that to happen. And so you go to great lengths to secure yourself against that by using formal verification, or at the very least, aggressive assertions, et cetera, et cetera. In a distributed system, you kind of don't care. Sure, there's some important processes, like you don't want your master node and your Paxos system to go down ideally, even though it would recover from it. But really, it's the communication topology between nodes that matters more, and the ability to recover those connections between the nodes. And the failure of one, ideally, is not catastrophic if you've architected your system correctly. And I think that sort of gets back to a lot of the theme that kind of is recurring, which is, the programming languages need to increasingly be about helping you to build correct distributed systems. Just as programming languages today, compared to 10, 15 years ago, help you to build correct concurrent systems. And we really haven't seen that, and the question is, it's harder. It's much harder because we get into the JSON question. It's a polyglot world. Like, everything is heterogeneous. Everything speaks a different language. And so how could you possibly have a language that helps you to bridge that gap when the thing on the other side of the connection may be written in a completely different language? The type system really can't span many processes or many nodes in a cluster. Or if it does, we need to have some sort of type system of the internet, if you will, that everybody agrees on, ideally something that's much better than JSON. So I won't say that this is a solved problem, but I do think this is a problem that programming languages do need to solve, ideally quickly.
Something that's interesting to me along those lines is, so we've been talking about, sort of broadly speaking, guarantees, and we've talked a lot about like type guarantees, but there are other guarantees that can or cannot be baked into a language, and they have different trade-offs, especially when it comes to things like concurrency. Speaking again in terms of Elm, so like in Elm, everything is immutable and everything is a pure function. You can't write functions that have side effects when you call them, and you can't write functions that mutate anything. And so this rules out a lot of possible concurrency-related problems. So Evan, if he were here, I guess he would say, because I've heard him talk about this in the past, there are lots of different ways with handling problems of what happens when data changes in various ways. So like you've maybe heard of like reactive extensions and streams and like event listeners and things like that to sort of react to the idea of data changing in a somewhat imperative, somewhat functional way. But Evan makes the point that if you just say everything is immutable, then you sort of don't have that problem because you substituted it with a different problem. The different problem is that you sort of have to rethink how you're going to write your code. But once you do learn how to write code in that different style and you get comfortable with it, then all of these problems get sort of ruled out, right? You have this guarantee that you can't have like a concurrent modification of the same piece of data because all of the data is immutable. You just can't do that even by accident. And so it's interesting to me to think about, as languages evolve, how much of it is going to be trying to find solutions to these problems within the current set of features that people are accustomed to, and how much of it is going to say, look, if we draw these guarantee lines in a different place, can programmers adapt and just learn how to get comfortable programming with this different set of rules where these problems can't happen anymore?
So, Joe talked about how languages need to get better at helping us solve distributed problems. And in the short term, I'm not seeing an awful lot of evidence of that happening in the mainstream programming community. And in fact, in some sense, I think we're going in the wrong direction, because as our program size on average gets smaller, because we're breaking up our programs into microservices or serverless or any number of programming paradigms that exploit the fact that network bandwidth is really cheap, and so you can break up your program into separate loosely coupled entities without a lot of cost. People tend to make their programming language choices on the basis of what's convenient for for productivity, what's easier for me to get this up and running. And so you see people choosing languages. I won't name any names, but some of the more popular languages in this space offer nothing in the way of Joe's three safeties, right? But that's what the market is choosing, right? So I think the availability of cheap bandwidth is in some sense making programming languages less relevant, which is kind of a shame, because I think programming languages have a lot to offer in terms of solving these problems, but short-term expediency sometimes outweighs the big picture.
Now, I will point out, there are some successful examples, and it tends to be in sort of the more domain-specific realm. So, Spark, for example, or just MapReduce generally. When you have a domain-specific programming language or programming model that is sort of a language plus some framework or libraries you use plus a runtime that takes care of scheduling for you, then you can have this nice, beautiful model that is consistent and has a richer type system and richer capabilities with it. The problem really is when you run into kind of the boundary of that system and you want to interact with other systems and it's more of an open-ended problem. I think that's kind of where things fall down today. And there's clearly a limit to how long you can stay within the confines of a very specific domain-specific solution.
So that's kind of interesting. You're going off into that way, but I heard a lot of different mentions on this around various qualities of service, like some people call non-functional requirements. Yet we don't see a lot of that being addressed. Like as we go forward, performance is clearly becoming more of an issue, not just in raw throughput, but saving battery life. So we parse JSON on our phones, we're just going to eat our batteries. We do all of this in the browser, same sort of thing. But you also see it with reliability, with all sorts of other things. But for me, I spend a lot of time on performance. We look at how hardware is going. Bandwidth is going up generation by generation, sometimes doubling, sometimes going up orders of magnitude. Accumulated latency, we're not getting any better. We're not seeing any evolution in APIs at a significant level within languages or their runtimes that we need to go async. It's not happening. Why are people not doing that?
Use asynchronous languages, they exist.
Yeah.
But to be more serious in terms of that, I think that performance is incredibly critical, and people often dismiss it and say, well, my particular application doesn't need to run fast. It may not need to run fast, but it absolutely needs to run cheap. And that means that performance should be a consideration for every possible application. And cheap on a phone is about battery life. It's about what you can conserve so that you can run longer. And that means that the only thing better than fast code is no code at all. And some of the techniques that we've been talking about up here, like type systems and memory safety, and even going all the way to formal verification, involve taking things out of the dynamic world and putting them into the static world, things that you can solve statically so that they simply don't have to be checked at runtime. That's a big deal. As much as async is a big deal, and I think it is, those lifting things into the static world is how you get to more asynchronous and faster programs.
Also, interestingly, what we found in the Midori project, it was interesting because it was essentially, you can think of it as every process was decomposed into a very fine-grained process, but you can think of it as more like a container sort of connected through RPC, and the whole system was built this way. So like the file system itself, was a separate process, and the NIC driver was a separate process, and it was all kind of message passing. And interestingly, with a aggressively optimizing compiler kind of behind the scenes. But interestingly, this trend towards finer and finer-grained processes actually has one advantage to it from a performance standpoint, which is smaller GC heaps, and GC heaps that can be collected independently of one another. We have fantastic parallel and concurrent GCs, but nevertheless, there's shared data structures whenever you need to do a collection, even in the most advanced parallel garbage collector. And actually having independent heaps that can be collected independently helps the overall throughput of the system and forward progress. And so I think that there are many disadvantages to the trend towards smaller and smaller processes, but that's one of the advantages.
So to the question of why, like how did we get here, I have a theory that involves two languages and how they got popular. So one language is JavaScript and the other language is Ruby. So JavaScript, I claim, got popular, not because of any intrinsic merit to the language itself, but just because the web got popular. Like browsers blew up, it's an amazing deployment mechanism. You type in the application you want, you press enter, and then you've got it, and no installation, nothing. It's hard to compete with that. Like you can't really do better than one step. That's the next step is 0, and then the computer has to read your mind to get you the application faster. So I think doing that caused JavaScript to get popular because that was sort of the only way you could get that application deployment experience. JavaScript's single-threaded, right? And it's not really optimizing for any of the things you're talking about. It works with strings a lot, and so people sort of made progress in JavaScript. Like if you remember how JSON originally, came to be, it wasn't that browsers started off writing native C extensions to parse JSON as fast as possible. It was that Douglas Crockford said, I want a thing that does this thing. I've got strings to work with. I'm going to invent this format. And that was it. And then it got popular. Similarly, Ruby, also single-threaded, was not a very popular language until Rails came out. And the thing, as I understand it, that popularized Rails was about a 20-minute YouTube video saying, check it out, I can make a blog engine from scratch in 20 minutes using this thing called Rails. And at the time, a lot of people were feeling like, I can't build stuff that fast. It's a lot of ceremony, it's a lot of setup time, it's just not as fun. And we're programmers, we like to have fun. So people gravitate towards that. They say Rails is something that will let me enjoy programming. But I think both of these put together make it so that it becomes more normal and more acceptable to have single-threaded stuff that's not focused on performance. Like Ruby's not performance-focused. JavaScript wasn't for a very long time until the browser wars of 2008 when they sort of started fighting over optimizing this stuff with JITs as fast as possible. But in both of those cases, talking about what the market wants, I think the fact that Ruby and JavaScript became normal programming languages, and you saw Node.js, come out of JavaScript's, ubiquity on the front end. All of these things are sort of coming together to make it the idea that this is fine, this is normal, everybody can get stuff done in this way. Performance isn't that important. Latency is not something we need to worry about. And yeah, maybe over time we will come to regret that. But I think that does answer the question of why, at least to my mind.
And to follow up on that story about Ruby, so it illustrates the fact that I think we're only looking at half the story. We're looking at the developer-facing half of the story when we make some of our technology selection choices, right? So Ruby got was around for a very long time. It was this minority thing, and then all of a sudden, when Rails came out and got popularized, Ruby really caught on, and people loved it. It made it really easy to incrementally build a data-driven web application, in one little bit at a time, and it was great. But it performed terribly when you went to deploy it. And so Twitter had an interesting story where they had originally developed most of their infrastructure in Ruby. They felt like it gave them a big productivity advantage doing so, but then when they started to get popular, they were adding up what their computing bill was, and it was astronomical. And they went through a process where they rewrote everything in some combination of Scala and Java running on the JVM, and their hardware cost went down by over a factor of 100. I say that not to trumpet Java's success, even though I'm sort of obligated to by my employer, but to point out that that when people talk about Java or C# or any language ecosystem, there's the source language you program in, which is what we as developers are obsessed with because we spend all our time looking at code, and then there's the runtime, which is really kind of the important part, right? And that's where all your deployment economies come from. It's where all your debuggability comes from. It's where monitorability comes from. It's where serviceability comes from. But as developers, because we're focused on code, we think the surface language is really the important part. But in a lot of ways, runtimes matter way, way more than programming languages do.
Yeah, this is reminding me a funny story at Microsoft. So we were porting an existing system, which is actually used for mission critical things. So in this case, it was the real-time bidding engine for Bing ads. And it's a large-scale thing. So on a regular basis, every hour, it crawls terabytes and terabytes of data. And what we found was for every 1K of data that actually was persisted on disk, the program would allocate 8K of just garbage objects, so strings and this. And what it was doing was actually loading up something off disk, parsing a blob of JSON into memory, splitting the JSON by looking for commas, which of course allocates a bunch of substrings into an array, which itself is another object, and then continuing to go on and do this. And so this was running across terabytes of data. And it turns out this was, you could have written this terrible code in any language, really. The framework itself, so building on Brian's point that the runtime is important, the framework and the library itself is also very important because it kind of encourages a coding style. So if you walk up to the string API in C#, well, it's got these handy dot split methods and so on and so forth that will happily allocate tons and tons of memory on your behalf. So this is an example where the language and the framework can help. I love Go slices for this reason, where you can actually just say, hey, no, I just want these few bytes in the middle of a string and not have to allocate an entirely new substring.
Yeah, I'd like to actually pick up on that because it's a lot of what I've seen and measured. Many performance issues I see in the wild are API design and not fundamental language design, yet it doesn't seem to get anywhere near the same love. Like, what can we do to get better at that?
Well, I think static analysis can help. I think having the right fundamental primitives helps. I mean, that's why I mentioned the Go thing. Before I left Microsoft, I spent 2 years leading up to the time when I left, and I think it will finally ship in C#7, potentially, adding slices into the language. But it's so hard to retrofit after the fact because, at least Go had them from day one, where an array is a slice, a string is essentially just, a slice of UTF-8 bytes and so on and so forth. So all of the APIs were built around the right fundamental concepts. It's hard to recover that after the fact. All of the .NET APIs except strings. The streaming APIs, for example, take a byte array. And so if you walk up with, byte star, well, okay, now you need to copy into managed memory. So some of those fundamental things you have to get right from day one. But a lot of it you can catch through static analysis and just sharing knowledge. It needs to be part of the culture of the language. Like that is one thing I like about the Go culture. It's very minimalistic and very attuned to these sorts of challenges. Like it is overly minimalistic. I think it's closer to C than say modern languages. But that is one thing. It's embedded in the community. So I think people just kind of are on the lookout for that sort of thing.
Cool.
And so following up on language community culture, so Strustrup said language design is library design and library design is language design. And what he meant was we tend to think about, when we're thinking about language features, we tend to think about, well, what kind of libraries do I want to be able to express easily? Right, so the natural APIs that you can write in a given language and the features of that language are pretty much inextricably bound. And if you're good, you will actually think about that explicitly rather than implicitly when you're designing things. But languages do tend to encourage certain kinds of API patterns, and so if you have, as you say, the wrong primitives, you're going to build the wrong APIs.
Any hope of NIO getting better in the future, Brian?
Sure.
It's been a while. Okay, at this stage I'd like to open it up a bit. And do we have any questions from the audience? Yeah, one over here. I'll run around if we've got a microphone over there.
Thank you. I would love to know, if you exclude your own languages, the ones that you've worked on, if you could pick another language as your everyday workhorse language, which one would you like to work with and learn and play with, and why?
I'll go. Clojure. Basically because everybody I know who's working in Clojure is just so happy about it that, you know, that looks great.
I think, strangely, not that I want to use it, but that I want to learn from it. It's Excel. Excel has 500 million programmers. Just let that sink in for a second. It's also a functional language and a functional reactive programming framework that's been highly effective for about 30 years. We have a lot to learn from Excel, strangely. People can approach it and use it. They have fun using it, which I think is a theme from what Richard's been talking about that's hugely important. I don't know quite how to learn from it, but I think I should.
So I do program every day now. I left my management job and I'm actually down in the trenches now. And I picked Go for that, mostly as a detox after having spent many years working on advanced type systems.
I'm going to say Rust. One of the things that's interesting to me is sort of like language identity and like what's the language about. So I think Elm is about sort of like delight and maintainability and reliability. Rust is like very focused on be as fast as possible and be as not broken as possible. They would probably express that more eloquently. But I'm really interested in those things because it's, in some ways, sort of like the opposite end of the spectrum of like what I'm doing with Elm. But I'm very interested in the idea of what if you're just saying, let's go as fast as we possibly can, but still not break things. What's it like to work in that environment and like optimize those things? And that sounds like a lot of fun to me for entirely different reasons than Elm was fun for me.
Cool. Any more?
Thank you for this panel. It's very interesting. I find it interesting that you've talked a lot about languages being important for distributed programming, typing, etc. Yet nobody's mentioned anything about paradigms like object-oriented or functional or any of these things. Do these things not matter anymore for future languages?
I think the thing that at least Joe and I have brought up is something else, a slightly different paradigm, which is actor model programming. And it's somewhat related to those things. I personally think that it's quite easy to craft an explanation of object-oriented programming that sounds like functional programming and vice versa. So that particular distinction doesn't fascinate me. But the distinction that does fascinate me there is ideas around memory safety. And I think if you think about it as a memory type and concurrency safety issue and think about actor model programming as a paradigm, then it does still matter. And a lot of times now you're looking at the difference between CSP, communicating sequential processes, and the actor model. Much like object orientation and functional languages, they are dual, but they do lead to different designs for systems.
Next one.
And I think the OO versus FP thing is largely a false dichotomy, right? And so, you know, one of my mentors once said, you should learn OO, you should learn FP, and then strive to rise above them both, right? And I think we all have something to learn from both of those paradigms, and if we align ourselves with, I'm a functional programmer, I'm an object-oriented programmer, you're missing a lot.
Next question.
Thank you very much for your time, as well as your talk. I just had a question. In couple of last week, there was some kind of conversation over the net about AI and the University of the Cambridge and Microsoft. They both together, they done some nasty stuff. Now AI can actually write some line of code, I think up to 5 or 6 lines to solve a problem. Do you think the future of the language programming is going the way that instead of we come with a better language for ourselves to solve the problems, maybe we should come with a better language that AI can use it in a better way? And if it does go that way, then how does it impact our career as a coder?
So that work is Mark Brockschmidt's work at MSR Cambridge, Deep Coder. And it is indeed given a set of inputs and outputs synthesizing code, and it is pretty magnificent work, in my opinion. I don't think anyone should be worried about their job too soon. Also, the programming language is a UI to the runtime, sort of touching on what Brian was saying. And yes, an AI needs a UI to a runtime, and perhaps that looks like a programming language, and perhaps there are different ways to build UIs to runtimes that look a bit different that are appropriate for AIs. For example, an AI might be more comfortable in Forth than in a lot of other languages. However, as a programming language designer, looking to expose a runtime in an efficient and useful way, focusing on how an AI would use a runtime, it doesn't motivate me, if that makes any sense.
I also think, before I left Microsoft, I was working with some folks in MSR as well on basically using deep learning to teach machines how to write code. But one of the challenges is when you're teaching a machine how to learn to solve a problem so that it can write the code, the representation of that learned artifact is not necessarily easily transcribable into code. And so I think the more interesting thing is code as we know it actually the correct intermediate representation for the interface between a neural network and the machine, given that the neural network is a network of weights and mostly opaque in terms of our understanding of it. So I think a lot of research over the next however many years it takes is going to be around teaching neural networks to interface with computers, and it's just not clear to me that that will look more like code than, say, an opaque assembly language, for example.
That's it.
One final question. Quick
Okay.
answers, please.
So we've heard a lot about strong typing being important, both for data types and functions and return values and so on, and of course asynchronous code for concurrency. But how do errors handle in this as well? Is strong type for error handling important, or for asynchronous error handling?
Yes.
Very good.
Perfect. So thank them all.
Thank you.